Please welcome back to the stage, Erik Ziehm.
All right. Hi again, everyone. So yeah, I'm Erik Ziehm. I'm a postdoc under Dr. George H. Miley in the Nuclear, Plasma, and Radiological Engineering Department at UIUC. So I'm going to be presenting a little bit from my PhD, which I covered LENR. And some of these results focused on alpha particle detection using CR-39 during a deuterium DC glow discharge with palladium electrodes. So first things first, what's LENR? I really wanted to just define what that is, and to do that, I'll use two example experiments. The first is done by Cecil in 1990, where they implanted high-energy deuterons into a 1-micron palladium film. And at these high energies, you get your typical DD fusion reaction byproducts, which they monitored using a silicon surface barrier detector. Then they turn it off and then apply a electric current. So there's nothing's incident on these foils. So your interaction energy is more or less room temperature. You'd expect 0 fusion events. But they measured 3 MeV and 5 MeV particles. Very atypical, not even the traditional DD fusion results. The second is chambers. They used low energy ions of deuterons incident on a titanium foil, also using an SSBD, and they also measured 5 MeV particles. I particularly like this one quote of, "The reaction we have observed can only be due to a novel, previously unobserved nuclear process involving deuterium." So we have low interacting ion energies plus unconventional nuclear products. That leads to the name low energy nuclear reactions. The low energy is solely on the interacting ion energies, not the byproducts, which is a common misunderstanding. So I focus on plasma material interaction. That is deuterium discharge interacting with palladium cathodes. On the right is a little figure just depicting how do deuterons impact the surface and lead to defects. And those defects then trap the deuterons. And I did a thermal desorption spectroscopy to show, oh, these bound deuterons don't exit the lattice until about 450 degrees Celsius. So we know that there's bound deuterium inside of this lattice. And the hypothesis is these clusters are necessary for LENR. So then with my methodology, reviewing the field, I saw a lot of reproducibility problems, not just in the prior 2 experiments, but all across the field. And that's mainly, well, the mechanism's still unknown. So I wanted to keep it simple. And like when you're investigating something that shouldn't really exist in nature, you want to keep it as simple as possible. So to do that, I used CR-39 and a DC discharge. On the right is the discharge diagram, where the detector is just that piece of CR-39, and I'll explain how CR-39 operates. So using this methodology, I wanted to focus on making direct observations as precisely as possible. And then from those observations, make abstractions and see if you can make inferences from those and see if they will be consistently corresponding between them. And then hopefully you can get some avenue for future work. I didn't focus on any type of partial theory or modeling or predicted phenomenon. This work was more or less a stepping stone to kind of use as a robust check for future theories. So why not an SSBD like these other groups? Why CR-39? And the entire reason is mostly no external electronics, sensitive to noise. I am using a DC discharge, and it does often go into noisy regimes, and that will influence your electronics. So CR-39, it's just a polymer. When an energetic charged particle is incident on the surface, it travels through it, penetrates it, it causes ionization. The ionization will lead to polymer chain breaking, and then you can etch the surface. That damaged volume is preferentially removed compared to the bulk. That leads to tracks. And then you directly observe those tracks. This is an example of 3.5 MeV alphas with an optical microscope. So if a nuclear reaction produces energetic charged particles, that will damage the CR-39 and lead to tracks. So my objective, determine experimental conditions that repeatably produce LENR. Great. So deuterium discharge plus CR-39 detector is about 5 centimeters away. Shocking, tracks appear. Okay, so you've got some tracks. You have to quantify the size of these tracks. You can even do 3D depth profiling to get a little bit more information. But you need to calibrate how does this detector respond to known ion sources. And I'll cover that. But we conclude that these tracks were consistently corresponded to roughly 100 keV alpha particles, helium, emitted from the palladium electrode. So we currently don't know any mechanism that would accelerate ions to these energies. Hence, we conclude some sort of nuclear process occurred. So the procedure, I'll just go through this quick. You have your CR-39. You do a deleting etch to remove the first 100 or 200 microns of material to make sure you get rid of your background. You do your radiation test, or you do your experiment. You do a track etch. My parameters were shown there. And then I designed, built, programmed an imaging apparatus to image these entire surfaces. Like these are 2.5 by 2.5 centimeters. And that's a lot of area to image at a micron resolution. So I wanted to automate that. And like this is an example of my autofocus. It's just looking for, let's optimize the sharpness, take an image, go to the next position. And then you can stitch those together to get a nice big image of your total surface. So then with that image, these things are like gigabytes in size. I didn't want to just sit there and looking at the image waste my time, so I used this freeware Elastic. It's a supervised machine learning for image classification. So it removes the human out of it once you train the software. So this is just a raw image. You say this is my green is background, red is foreground. Then you can threshold these local pixels into objects. And then you classify those objects based off of their shape, color, relationship to one another, and then you can export the tracks. And then I get what I call a track density heat map to see where are tracks occurring on my chip. So now we're at what caused the tracks. It could be protons, alphas, or some other ion. It could even, I hypothesize, well, maybe it's plasma radicals or surface charge effects. I wasn't sure, so we just have this observation of small, shallow tracks in CR-39. On the right, the far right, are examples of tracks from other ions. So we have to rely on the calibration of the CR-39 to really extract what is causing these tracks. So with the calibrations, I used americium and an air gap, just measuring the distance between my detector and my alpha emitter up here, and then you calculate using the transport of ions and matter to see how much energy is lost as these ions penetrate through air. An example of just 5.5 MeV alphas is on the right, and the very first calibration is measuring that minor axis for the track versus its energy. So when you attenuate the incident energies, then you measure their resulting tracks. So that's one. Then another is let's etch these things multiple times. See how how each energy interval progresses with 1 hour etch, 2 hour etch, 3 hour etch. And you can do the minor axis versus incident energy for each etch interval, and then kind of as a corollary, measuring the slope. How much does the minor axis change with etching time? And then another one is track depth. And I wanted to do this because particles can produce the same track diameter, but they would have different depths based off of their stopping power. So that would be able to discriminate between, say, an alpha or a proton. So I'm mainly, again, looking for consistency. If tracks are due to protons or other ions, then a discrepancy will be seen between the metrics. Here's an example of my 1-hour etch calibration with example images of tracks. The tracks from the plasma experiments are about 8.5 microns. So I focus on the lowest 5 energy intervals, and that goes to 120 keV incident energy estimates. So now going to just track counting, how many tracks are occurring for each experiment. This is a graph for just track density versus fluence, which is how many ions are interacting with my electrode. It doesn't take into like secondary electron emission or backscatter. But the black is the deuterium, and then red and blue are my controls with hydrogen and helium. And deuterium was typically about 100 times higher in track density than the controls. This is an example of a hydrogen track, and then this is, as the fluence increases, it saturates the detector. So moving forward, this is now an example of, here are my tracks. Let's throw it through the gamut of all these measurements. So here's the histogram for all my tracks, their minor axis. They appear monoenergetic. Let's look at the calibration curve. That leads to 120 keV. Then let's do the progressive etching. After each etch, you measure, you export, and then you compare it to the calibrations. These are calibration curves for my americium source tracks for each etch interval. And for each one, it always corresponded to roughly 120 keV. I also measure the slope of the minor axis versus etching time. So it's a little different, but it also leads to the same conclusion, roughly 100 keV. Now, depth profiling. I manually measured 200 tracks. That was a lot of fun. And I also did that for all of my calibration tracks from americium, do the fittings, all that fun stuff, 93 keV. So what else can be extracted from the 3D measurements? As I was doing that fun depth profiling, I'm like, well, these things are conical in nature. On the right is a depth profile with a bunch of fittings, and you can bifurcate the walls, so divide it in half, and that can even give you an estimate of where is this particle coming from that hits your track. So I scanned 2 samples across 3 y-axis positions. That's a lot of measurements. And then I back calculate trajectories. On the right is just a little graph of all of these trajectories, and it's, oh, interesting. They seem to converge. This is a cross-section, so a 2D projection of that 3D data at the z equals 5. That's where my electrodes are located. And oh, they're all pointing towards a similar point of origin. So that is evidence that, okay, these things are coming from my electrodes. So that removes the possibility of, say, cosmic rays or some sort of galactic event or atmospheric radon, just like depositing on my CR-39. So in summary, I'll go over, we've got shallow tracks. We've got our minor axis versus incident energy calibration curves relying on americium. That leads to 120 keV alphas. We've got the track etch progression. That leads to roughly 120 keV incident alphas. The slope, roughly 100. The 3D profiling for the depth, that was roughly 100. But I also used that same measurement to kind of check my optical automated analysis. So now, like, I was measuring these manually, the diameter, and that was roughly 100 also. Then there were other experiments just replicating z equals 5. That's the distance between my detector and the electrodes. Do the same stuff, roughly 100 keV. Now, I then use TRIM, the transport of ions in matter, that takes into account how much energy is being lost as these ions traverse a pressurized vessel. That would be 5 centimeters in 10 torr of deuterium. So you back calculate that, that leads to, oh, they were emitted from the electrode at around 138 keV from the cathode. Now, I didn't show any of this. Now this is stuff that's just supplemental that was from my PhD. Let's move the detector back to Z equals 10. Do the same thing, lower incident energy, but you do trim through 10 torr of, at 10 centimeters, shockingly 138 keV, right on the dot. And then from this data, you can also do solid angle dependence to estimate emission rates. How many tracks are being produced per unit area per unit time? And those also corresponded well together. Now, this one is a whole bunch of other stuff, but the main thing is this, the question, what else might be causing these tracks? Plasma radicals, or maybe some sort of surface charge effect is accumulating that's leading to these tracks? And to kind of address that issue, well, I just sputtered a whole bunch of gold. Well, first one was 100 nanometers, and shockingly, there were tracks. There were a significant amount of tracks, so that kind of removes the plasma radical hypothesis. But simultaneously, I had unshielded detector in there, and that one had larger tracks, roughly incident energy of 122, whereas with the one with gold, they were attenuated, so roughly down to 100 as they lost that energy as they went through the gold. You can do trim again to say, okay, now take this input into trim, has to travel through 100 nanometers. What's the resulting energy? Roughly 90. Okay, 90 compared to 100, that's in fairly good agreement. And it also gives you information on ions with similar stopping powers in CR-39 can produce tracks that look almost identical. Two possibilities were palladium ions somehow getting accelerated up to 5.5 keV, just saying, okay, sure, they might be getting up to that energy, but they'd have a very low penetration distance in that gold. So that removes palladium, and the helium-3 is still potentially a cause. I have not been able to discriminate that. As for the 500 nanometer of gold, reduced back down to more or less near the controls of track densities. So that removes the possibility of these being, say, protons. They'd be able to traverse that 500 nanometer thickness of gold and then cause tracks. And then just the normalized track density for my controls were consistently 100 times lower than what I was doing with deuterium. So that also gives supporting evidence that plasma radicals and surface charge accumulation did not cause these tracks. And then last with the 3D profiling for the track trajectories. I designed, built, programmed this imaging apparatus and analysis pipeline for automated track detection, and I calibrated my CR-39 with americium-241, and then I did extensive experiments to establish charged particle emission that was consistently corresponding to roughly 100 keV alphas, which is noticeably different from the 5 MeV particle group from Cecil and Chambers. So what's going on? Well, pretty simple explanation. They used shielding to block their SSBDs from any kind of stray plasma radicals. And that shielding was typically, say, 10 microns of material. That's going to block all of your low energy alphas. So that's pretty quick. And it was repeatable. I don't have the slide up here, but I did the same test with deuterium, get the tracks, evacuate the chamber, bake it out, make sure I release all deuterium from my electrode, and then do it with hydrogen, no tracks. Then do the same preparation procedure, do it again with deuterium, back to tracks. So that 100 keV is kind of similar to the DD gamma helium-4 reaction pathway. However, I was always monitoring for neutrons. I never saw any kind of elevated neutron counts. That being said, it is neutron detection was electronically based, and the entire reason why I used CR-39 was to get past noise. So noise could have affected my neutron diagnostics. So we've got a plasma that has a maximum incident energy of roughly 550 electron volts. That's taking it to the extreme. It's Maxwellian. It's really, the average is much, much lower. But we're just being conservative. And we've got these unconventional nuclear products. That leads us to, well, we think a low-energy nuclear reaction occurred. And then I just want to quickly show this before I end recent work on DC stimulation, where I do the plasma treatment with CR-39 away from my electrode with a valve closed, and then turn off this plasma, put the CR-39 in close, apply a DC current. This is just a little artistic representation of bound deuterons and defects, and you've got a deuteron current going through there. And shockingly, tracks appear again. And they also were consistent with roughly 138 keV alphas. So that's very interesting. And so just concluding remarks for the new people in the audience, it wasn't easy getting my PhD in this field. I started off, my committee was very skeptical, to say the least. But please just be stubborn and have fun with it. And at the end, my most skeptical committee member was like, Erik, you just convinced me that something is really to this field. Like there's something really going on. Like it's hard to refute all of this evidence. And that felt great, but it was really just great. I had a lot of fun doing this stuff. So thank you, and some questions.
This was a beautiful presentation and great work.
Thank you.
Just a couple of comments. I really like the use of the 500 nanometers of gold to basically show that it was not alphas. But the second thing is the work of Segwin and others at MIT and others that we've worked with indicate that you do not get a CR-39 response for basically less than 100 keV per nucleon. So you've got two charged nucleons. That would mean to detect an alpha, you'd need on the order of 200 keV.
Yeah, my response would be I don't have access to that low of an energy ion gun, right. But my literature review said the threshold was much lower.
So the other comment is you can use feather methods such as you did, put absorbers between, and in fact, Pam Mosier-Boss and I have published some papers on doing this to calibrate down to 1 MeV, but clearly you could go below that. And I really do appreciate what you've done. This is good work.
Yeah, like, so when I was doing my calibration curve, I went down all the way to 200 keV. And I still had tracks, and it was still, the minor axis was still decreasing. So yeah. Next.
So Erik, we have time just for one more question.
Okay.
Just one small question. Do you have any idea to get a reaction rate from your?
Yeah, so that's the question right now is reaction rate. We don't know if it's in bursts, if it's continuous, because CR-39, it's a dosimeter. It's accumulating these tracks. So right now, I just have an average. So I do not have a reaction rate, but that's top of my priority to try and figure out. Yep. Thank you, everyone.
Erik, thank you.